Hello everyone. This is the second session of the chapter Kinetic Theory. In this session, firstly we will be deriving the expression for pressure of a gas based on the kinetic theory of gases. For this, we will be considering a cubical container which is filled with an ideal gas, and let n be the number of molecules inside this container. We know that from the kinetic theory of gases that the molecules are under random motion. While moving, these molecules can undergo collision with each other as well as with the walls of the container. If the molecules are undergoing collision with the walls of the container, they exert a force on it. So the force exerted by these molecules on the walls per unit area is called as a pressure of a gas. So we have defined here pressure is nothing but a force per unit area, which is the force exerted by the molecules on the wall of a container per unit area. Now, to calculate the force on wall of the container, first we need to consider a molecule, a single molecule. So this molecule can have a motion along x direction, y direction or z direction. It is free to move inside a container. And let us write the velocity of this particle as v is equal to vx I cap plus vy j cap plus vz k cap, and its magnitude is given by v square is equal to vx square plus vy square plus vz square. Now imagine this molecule is moving towards this wall, and after undergoing the collision, since the collision is completely elastic, we know that from the kinetic theory the collision is completely elastic. What happens is this molecule, after undergoing the collision with this wall, it reverses its direction and it moves with the same magnitude of velocity. Means if this molecule is moving with some 10 meter per second along the x direction, after undergoing the collision, its velocity along x direction is minus 10 meter per second. It only changes its direction or reverses its direction without changing the magnitude of velocity. That is what we call as elastic collision. Now, the magnitude remains the same, only the direction along the x-axis is reversed. Therefore, the velocity is now been written as minus vx I cap plus vy j cap plus vz k cap. From this equation, we have vx I cap here. After the collision, it is reversing the direction. Therefore, the final velocity v dash becomes minus vx I cap plus vy j cap plus vz k cap. There is nothing change in the y and z component of the velocity. Now let us write the change in momentum of the particle. We know that momentum is nothing but product of mass and velocity. So this is the final momentum and this is the initial momentum, and this is nothing but a change in momentum. So change in momentum is final momentum minus initial momentum. How to write the final momentum here? Minus m into vx. Why it is minus m into vx? M into minus vx. Minus vx is the final velocity of the particle after the collision. Therefore, it becomes minus mvx. Minus of initial momentum. M into initial velocity is vx along the positive direction. So, it is mvx. Now, if you write the change in momentum, the change in momentum will be minus 2mvx. Now, if you write the force exerted on the molecule, we know that force is nothing but the rate of change of momentum. So delta P by delta T. Delta P is this minus 2mvx. Let us substitute this minus 2mvx divided by delta T. Now, if delta T is the rate at which the molecule collides with the same wall, again, and it is given by, see, if the molecule has started its motion from this point and it is moved up to this wall and undergoing the collision, and it is returning to the same point, means it has traveled a length of 2L, correct? So the length of the cubical container from one side to another side is L. If it is returning to the same point, means the total distance becomes 2L. Therefore, the time taken for this is written as the distance covered 2L divided by its velocity Vx. So delta t is nothing but 2L by Vx. Let us substitute this delta t by 2L by Vx now. So minus 2 mvx divided by 2L by Vx. So force becomes minus mvx square divided by L. So this is nothing but the force exerted by the wall on the molecules. Now, according to the Newton's third law of motion, the force on the molecule is equal and opposite to the force on the wall of the container. Correct? So this force is written by saying that the force exerted by the wall on the molecule. Now, according to Newton's third law, the force on the molecule is equal and opposite to the force on the wall of the container. Therefore, the force on the wall of the container, force exerted by the molecule on the wall of the container, is written as F is equal to mvx square divided by L. It is just opposite to this force. But we have written this equation of force for a single molecule. Now, if we have n number of molecules in a container, how to write the force? This Vx will be having V1x square, V2x square plus etc. up to Vnx square. Because we have n number of molecules in it, this velocity is for all the molecules. So V1x square, V2x square up to Vnx square. So this will be the force. Now, if you say that the pressure on the wall BCGF is, see in this diagram, BCGF is the wall and there are n number of molecules in this container. All are moving towards this wall and exerting a force. And the force exerted by this n number of molecules on this wall is now written as F is equal to m V1x square plus V2x square plus up to Vnx square whole divided by L. And the pressure, so how to write the pressure? Pressure on the wall is now given by force by area. So force is this is a force divided by area of that wall. Area is nothing but area of that cube. Surface area of a cube is nothing but A. And this A can be written as L square. Because we have a cubical container, if L is the length, then L square will be the area. So we get this A as L square, and if you take this L to the denominator, it becomes L cube. Finally, the pressure will be m into V1x square plus V2x square plus etc. up to Vnx square whole divided by L cube. Now, as the molecules of the gas are free to move in any possible directions, the pressure in the container is the average pressures along x, y and z directions. Means the pressure is not only exerted on one direction, it can be exerted on all the directions. Therefore, the pressure is having a components like this. P is equal to P1 plus P2 plus P3 whole divided by 3 along x, y and z directions. So, if we substitute this, we get P is equal to m divided by 3L cube. We have just written 3 here. So we have just divided by 3. So m divided by 3L cube into V1x square plus V2x square plus up to Vnx square. Now we have to write the components of y and z components also. The velocity along x, y and z components. But the magnitude of velocity v, we have written v square is equal to vx square plus vy square plus vz square. So if you add v1x square plus v2x square plus v1z square, we will get v1 square plus v2x square plus v2y square plus v2z square will give us v2 square. In the same way, vnx square plus vny square plus vnz square will give us vn square. Therefore, the pressure, the equation of pressure now becomes m divided by 3 into v. So this is 3 into L cube. L cube is nothing but the volume of that container, so which is written as V now. So m by 3V into V1 square plus V2 square up to Vn square. Now let us multiply and divide by the number of molecules n to this equation. So m into n divided by 3 into V, and divide this quantity V1 square plus V2 square up to Vn square whole divided by n. So we are just multiplying and dividing this n, so nothing will change. Now this n by V, the number of molecules present per unit volume V, is written as small n, and this quantity V1 square plus V2 square up to Vn square whole divided by n is taken as V RMS square. This RMS is nothing but root mean square velocity. Okay, this is nothing but a average velocities of all the particles, V RMS square. We'll discuss this about later. So we just write this quantity as V RMS square. Therefore, the equation of pressure becomes P is equal to 1 by 3 into, so we are keeping this 3 as it is, so 1 by 3 into m, keep this m as it is, and n by V is written as n, small n, so n into this quantity is nothing but VRMS, so P is equal to 1 by 3 mn into VRMS square. So this equation gives the equation of pressure of a gas in a container where n number of, where this n is the number density, so this n is called as a number density, that is number of molecules present per unit volume, and VRMS is the root mean square velocity of a gas molecules, which will be discussed later. So this equation gives the equation of a pressure. Fine, we'll move on to the next one now. So if I consider the same equation, P is equal to 1 by 3 mn V RMS square. So in this equation, if you write this n as n by V, okay, if you replace this n, number density of molecules, as n by V, 1 by 3 into m by V. So this m is nothing but multiplying m into this n. M is nothing but mass of a single molecule. N is the total number of molecules. So if you multiply these two, you will get the total mass of the gas. So m into n gives us m, and this V is kept as it is, V RMS square. But mass divided by volume, m is total mass of the gas and V is the volume of the gas. So if you divide m by V, what you will get is the density. So pressure is given by 1 by 3 rho into V RMS square. So this is the one more equation. So pressure is equal to 1 by 3 into rho V RMS square, where this rho is called as the density of the gas. Now we need to understand this RMS velocity. What do you mean by an RMS velocity? See, if you consider a container and we fill the gas or an ideal gas, and we have n number of molecules in it. All the molecules may not be having a same velocity because of their collisions. Their velocities may be different. So if we say V1, V2, V3 up to Vn, so they are the different velocities of each molecules of a gas. So if V1, V2, V3 up to Vn are the velocities of n number of molecules in a gas, then the root mean square velocity is written as VRMS is equal to square root of V1 square plus V2 square plus V3 square up to Vn square whole divided by n. So we consider, even though the particles, all the molecules are having a different velocities, on an average all these molecules will be having some same velocity. So that average velocity of all the molecules in a gas is called as this RMS velocity. How to obtain the equation for RMS velocity? What we need to do is, first we need to consider the velocities of all the particles. You should square them and add them. So squaring and adding all these velocities and divide it by total number of molecules, and then take a square root of this. So this gives us the RMS velocity. So what is RMS velocity? Root mean square velocity, which is the square root of the mean of the squares of the all the velocities. Or if you just simply say what is RMS velocity? RMS velocity is the average velocities of all the particles or all the molecules in a gas which are moving with a different velocity. This is the average velocity. It's a single value. Fine. Kinetic interpretation of temperature. So if I consider the equation of pressure, the pressure is given by 1 by 3 rho into Vrms square, and if you write the same equation, the density is now been replaced by m by v, mass divided by mass divided by volume. The density is written as mass by volume. So m is kept as it is, 3 into v Rms square. Now take this v towards the left side. So we get p into v is equal to 1 by 3 m into Vrms square. But for 1 mole of a gas, m is equal to m into Na. So for 1 mole of a gas, the total mass is given by mass of a single particle into Na. Na is nothing but number of molecules present in 1 mole, which is nothing but Avogadro number. We know that. For 1 mole of a gas, how many number of molecules are there? Avogadro number. So for 1 mole of a gas, m is written as m into Na. And also PV is equal to RT. Here we have nRT, n is number of moles. So for 1 mole, n is equal to 1. So PV is equal to RT. Therefore, if you replace this PV by RT, so RT is equal to 1 by 3 into m is written as m into Na of Vrms square. Now, RT divided by, take this Na to the denominator. So RT by Na is equal to m Vrms square divided by 3. Now take this 3 to the left hand side. So 3 into R by Na into T. So we have just rearranged the equation. So take this 3 towards this side. So 3 into R by Na into T is equal to m Vrms square. Now multiply 2 on both sides. Sorry, this is actually 1 by 2. So you have to multiply 1 by 2 on both sides. So 3 by 2 into R by Na into T is equal to half of m Vrms square. But the quantity R by Na is nothing but, we know that R is a universal gas constant, Na is a Avogadro number. So when you divide universal gas constant by an Avogadro number, we'll be getting one more quantity or one more constant, which is called as a Boltzmann constant. So the Boltzmann constant is written as K subscript B. So this K is equal to 1.38 into 10 power minus 23 joule per Kelvin. So this R by Na is written as K, Boltzmann constant. Therefore, we get 3 by 2 kT. Okay. So we have just replaced this R by Na by K. So 3 by 2 kT. This is equal to half of m Vrms square. Now half m v square. Vrms is nothing but velocity. So velocity square. Half mv square is nothing but the average kinetic energies of molecules. So average kinetic energy of molecule is written as 3 by 2 K into T. So the average kinetic energy of gas molecules defines the temperature of the gas. See, the kinetic energy of the gas is equal to 3 by 2 kT. 3 is a constant, 2 is a constant, K is a Boltzmann constant. That is why the kinetic energy of the gas molecules is proportional to the temperature. Means if the temperature changes or temperature increases, how we can increase the temperature means if the kinetic energies of molecules increases, then the temperature of that gas will increase. Therefore, by explaining the kinetic energy of, or by knowing the kinetic energies of gas molecules, we can interpret the temperature of the gas. Now, if we rearrange the equation, so if we rearrange this equation, we can have an equation for RMS velocity in terms of temperature. So V Rms square is equal to 3 kT by m. So this m, you just cancel this 2 and 2 and take this m towards this side, and V Rms square becomes 3 kT by m, or V Rms is equal to root of 3 kT by m. So this equation gives us the equation for velocity or RMS velocity in terms of temperature. Fine. Next, Importantly, the results of kinetic interpretation of the temperature. So what are the important results of kinetic interpretation of temperature? So firstly, the kinetic energy of gas molecule is directly proportional to the absolute temperature. I already told you that by this equation, kinetic energy of the gas molecules is equal to 3 by 2 kT. So 3 by 2 K is a constant. So the kinetic energy of gas molecules is directly proportional to the absolute temperature T. Now, the kinetic energy of gas molecules is 0 when temperature T becomes 0. Suppose if this T becomes 0, if the value of T becomes 0, the kinetic energies of gas molecules is 0, which means the absolute 0 temperature, T is equal to 0 means it is the absolute 0 temperature. We already know this. So for an absolute 0 temperature, it is the temperature at which the molecules of a gas, the motion of molecules of the gas ceases. They are at absolute rest. Means if the kinetic energy is 0 means their velocity is 0. As their velocity is 0, they are at absolute rest. So when the molecules in the gas, see, if these molecules under motion, then only it is having some kinetic energy, and then only the gas possesses the temperature. If the molecules are at rest, they are not at all moving, means their temperature becomes 0. The molecules are they are not having any kind of motion, means the temperature of that body becomes 0. That is nothing but an absolute 0 temperature. So we have defined the absolute temperature by one more way now. The absolute 0 temperature is the temperature at which the motion of the molecules of the gas ceases. They are at absolute rest. Fine. In this class, we have derived the expression for pressure of a gas in a container, and then we have written an equation which is relating the kinetic energies of kinetic energy of gas molecules with the temperature, and we have written the results of this kinetic interpretation of the temperature. So in the next class, we'll be learning some more concepts of kinetic theory. Until then, thank you.